In this video, we will give the Thevenin equivalent of a circuit. The circuit on the right is the Thevenin equivalent of the circuit on the left. The circuit on the left is enclosed inside a box. It is made up of any number of resistors, independent and dependent sources, and it has two terminals A and B coming out of the box. We are interested in finding the equivalent of the circuit between the terminals A and B. The circuit on the left can be replaced by the circuit on the right, which consists of an independent voltage source of value Vt in series with a resistor of value Rt. The circuit on the right is also enclosed in a box, and it has two terminals A and B coming out of the box. And both circuits have the same behavior at the terminals A and B regardless of what is connected to these terminals. Note that the circuit on the left can be very complicated and have many resistors and independent and dependent sources. However, it can be replaced by a very simple circuit which consists of just one voltage source and one resistor. Normally, we will be given the circuit on the left and we will have to find the values of Vt and Rt for the circuit on the right side. The voltage source value Vt is called the Thevenin voltage, and Rt is called the Thevenin resistance. We will begin with the calculation of Vt first. Suppose we do not connect anything between the terminals A and B for both circuits, that is, to leave them open circuited. Since nothing is connected between the terminals A and B, the current through the resistance Rt will be equal to 0, and the voltage at the terminals A and B with the polarity given will be equal to Vt. Since the two circuits are equivalent, we must get the same voltage of value Vt for the circuit on the left as well. Therefore, to calculate the value of Vt, we do not connect anything to the terminals A and B and measure the open circuit voltage between the terminals A and B. Since the voltage Vt is calculated as the open circuit voltage between terminals A and B, the Thevenin voltage is also called the open circuit voltage. Once we know the value of Vt, we can calculate Rt next. We begin by drawing both of these circuits again. And this time we will put a short circuit between the terminals A and B for both circuits, and there will be a current flowing through this short circuit, and we will call this current the short circuit current, or ISC, for both circuits. For the circuit on the right, the current ISC will be simply given by Vt over Rt, or Rt can be calculated by dividing the Thevenin voltage by the short circuit current ISC. To summarize the calculation of Rt, we place a short circuit between the terminals A and B and measure the current ISC in the direction shown. Once we have calculated the value of ISC, then the value of Rt will be the Thevenin voltage, which is obtained in the previous circuit analysis with open circuit conditions, divided by the short circuit current, which we obtained from the analysis of the circuit with the short circuit, will give us the value of Rt. To summarize the calculation of the Thevenin equivalent of an arbitrary circuit at two terminals A and B, we first leave the terminals A and B open circuited. We measure the open circuit voltage between these two terminals, and this open circuit voltage will be equal to the Thevenin voltage. The next step is to put a short circuit between the terminals A and B and to measure the current flowing in this short circuit, and the value of the Thevenin resistance Rt will be given by the open circuit voltage divided by the short circuit current. It is also important to note the polarity of Vt and the direction of current flow of ISC, and we have chosen the directions such that if Vt is positive, then ISC will also be positive, such that Rt is positive, and if Vt is negative, then ISC will also be negative and Rt will still be positive. Closely related to the Thevenin equivalent is another equivalent circuit called the Norton equivalent, and we will give the connection between Thevenin and Norton equivalent next. For the Thevenin equivalent, we have shown that the circuit on the left, which is any circuit made up of resistors, independent and dependent sources, which is enclosed inside a box and has two terminals A and B coming out of it, then this circuit is equivalent to a single voltage source of value Vt in series with a resistance of value RT, and we have given methods to compute VT and RT above. The circuit on the left is also equivalent to the second circuit on the right hand side, which consists of a current source in parallel with a resistor. The value of the current source is Jn, standing for the Norton current, and the value of the resistor is Rn, standing for the Norton resistance. Since the two circuits on the right are equivalent to the circuit on the left, we should not be surprised to know that the two circuits on the right hand side are also equivalent to each other. In fact, if we look at them closely, they are the source transformation of each other. And for source transformation, we have that the two resistance values must be equal, and the voltage source value Vt is equal to the product of the resistance and the current source value. Also recall from the Thevenin circuit analysis that Vt over Rt is equal to the short circuit current Isc, which will also be equal to the Norton current Jn. And the open circuit voltage Vt is equal to Rn Jn. To summarize Thevenin and Norton equivalents of a circuit, we can replace any circuit at two terminals A and B by either the Thevenin or the Norton equivalent. Each of these equivalents requires the calculation of two values, either the Thevenin voltage and the Thevenin resistance, or the Norton current and the Norton resistance. And these two values can be found by first calculating the open circuit voltage between the terminals A and B, and then the short circuit current between these two terminals. We will take an example circuit in the next video and calculate the Thevenin and Norton equivalents.